we are asked to consider the effect on pH of adding a small amount of a strong acid to a buffer. This is the same acetate buffer we've been working with, 0.5 molar of the weak acid and 0.5 molar of its weak conjugate base. The added acid is going to react with the base part of the buffer. The base part of the buffer is the acetate ion. This is a strong acid, so it's going to react with everything possible there. After it reacts as an acid, it's going to lose its H+, and the result is water. As far as the base part of the buffer is going to accept an H+, and we regenerate a little bit of the weak acid. So essentially, the strong acid has been converted to a weak acid by the buffer. The concentration of the weak acid is going to increase a little bit, and the concentration of our weak base is going to decrease by an equal amount. So now that we have a general understanding of what's happened here, we have an added strong acid. It's going to react with the base part of the buffer, so it'll decrease a little bit. The acid part of the buffer is going to increase in concentration by an equal amount. Now let's consider the quantitative aspect. This is a buffer. We're going to use the Henderson-Hasselbalch equation. We know what the initial concentration are of the base and the acid. We don't know their concentrations yet after they have reacted with the added strong acid. We know the initial concentration of the acid and its conjugate base. We know the volume of this solution, so we can easily calculate the initial moles of our acid and its conjugate base. And since they have equal concentrations here at the start, they have the same number of moles at the start, 0.50 moles. Let's remind ourselves of the reaction that occurs. We're adding a strong acid. So we add a strong acid. It's going to react with the base part of the buffer, which is our acetate ion. It's going to react completely to form some acetic acid and water. We'll use a BCA table and keep track of amounts of things in moles. Initially, we have 0.50 of both the conjugate base and its acid, and we're adding 0.02 moles of our strong acid. All of our added acid is going to be consumed, and it's going to consume an equal amount of our base and produce that amount of its conjugate acid, so that after the reaction occurs, we have 0.48 moles of the base and 0.52 moles of the conjugate acid. Now we can apply the Henderson-Hasselbalch equation. When we use the Henderson-Hasselbalch equation, we can remind ourselves that the ratio of the moles of the base to the acid is the same as the ratio of those concentrations because they're both in the same solution. We input our values, and the numbers we get out are 4.74474 plus a negative 0.0348. And the resulting pH of solution after the added strong acid is 4.709, or with 2 sig figs, 4.71. Okay, remember our initial pH of the buffer was equal to pKa because it was a balanced buffer, and that was 4.74. So the delta pH is only a negative 0.03 units. So we see that by reacting the strong acid and converting it to a weak acid, we've had minimal impact on our pH.